Now, Shannon, as Professor Tishby explained, it tells you about the fundamental limitations to reliable communication over a noisy channel. Furthermore, there's a theorem which tells you what the architecture of this communication should be. Namely, there is a separation theorem. Namely, you should optimally do source coding, right? Compress the data as much as possible, and that you can do up to entropy. And then you can separate that from combating the noise that's in the channel. That's channel coding. So source coding is compression, channel coding is in some sense expansion, right? You add redundancy in some sense to combat the effects of noise. And then you can put the two things together, and that's optimal. However, as Professor Tishby explained, there's a cost associated to it in the following sense, that you have to do block length coding, or you have to allow infinite delay. And I bring in the third picture, namely statistical inference and statistical mechanics. Statistical inference is this construction of this x hat, right? There's some minimal sufficient statistic. Now, statistical mechanics comes into the picture, is that allowing infinite delay or making delays larger and larger, right? That's like, and asymptotically, you get this optimality of the separation between source and channel coding. That's like passing to a thermodynamic limit. And Shannon himself had speculated that when we understand information theory in its deepest form, it will be like thermodynamics. Okay. So one of the issues that I was interested in, I've been interested in, is that in what situations can you apply Shannon theory in some sense? Namely, this business of infinite delay. Firstly, can you prove the noisy channel coding theorem as a problem in statistical mechanics? And in joint work with Nigel Newton, we showed that, in fact, this passing to the thermodynamic limit in statistical mechanics has the exact analogy to passing to this block length coding limit. And you can view the noisy channel coding theorem as a problem in statistical mechanics, in particular Bayesian inference, if you like. By the way, in other work, we have shown that Bayesian inference is equivalent to free energy minimization. And free energy is the average energy minus the entropy. Now, there's some work to be done there, because the theorem in statistical mechanics requires stationarity, and in the noisy channel coding you will not have stationarity. But it turns out the idea of exchangeability is a very natural substitute for stationarity. Okay. Now, actually, I didn't see your slides before. So these fields interact, as I say, in the study of optimal stochastic control of noisy dynamical systems in the presence of noisy measurements. And I'm going to tell you about this Maxwell Demon as an example in non-equilibrium statistical mechanics, which is of recent interest. And one other point about Shannon's theory, I mean, Shannon theory requires, in some sense, there's no limitation to computation. And Shannon theory does not deal with resource allocation, in some sense, the availability of bandwidth or availability of energy, etc. So those are not part of the Shannon theory. In that sense, it's an idealized theory. And I think those things have to be brought into the picture. Now, what I'm going to talk about, I have lots of slides, but two things. One an explicit example of the second law of thermodynamics in relation to Landauer's work and how do you extract work from thermal fluctuations. That's one part. And the second question is this business of entropy flow, right? As Professor Tishby has explained, that from the source X, maybe some noisy source, you pass to some minimal sufficient statistic. Minimal sufficient statistic is in the general sense, is really the conditional distribution, say, of the source X given the observation. Or a better way to think about it is the map from the, say, the initial state and observations into this conditional distribution, right? So you have observations coming into, you're doing some sensing of the world, and observation is coming into this filter or predictor, right? And information is being transferred, say, from the initial state and the observations into the filter. What is the nature of this information flow? And interestingly, I think the next talk is going to talk about dissipation. And what I will show is that the filter, right, this extractor of maximal information from the observations, right, it stores that information that is necessary to do the prediction or the prediction that, or construction of the state at time, say, capital T, and it throws away information that is not necessary for computing the filter at time T or doing prediction at an optimal rate. And this, Professor Tishby has already mentioned the mutual information quantity, right, which measures the dependency between the actually neutral directed information, which measures the information between the past and the future. Now it turns out the rate at which this filter, the rate at which this filter discards information is governed by the so-called Fisher information, which I will show. And so in some sense, that forms a relationship between Fisher information, which is another information measure, with Shannon information. So that, in summary, is the title of my talk and the words that are in there. Now, there are many other situations that I will not talk about. Now, it turns out that the noisy channel coding for Markov sources can be viewed as a problem in stochastic control or dynamic programming. And this is joint work with my former student, Sekar Tatikonda. I will not talk about it. And the other issue is that when Shannon developed his theory in 1948, so actually two things happened in 1948. There was Shannon's paper that came out in the Bell System Technical Journal, and also there was the time of the invention of the transistor. And Andy Viterbi has called this the double Big Bang, which really created the digital revolution, the combination of this, the invention of the transistor and Shannon's theory. Now, Shannon himself warned in an editorial that this was a theory of communication of a particular model. So Professor Tishby mentioned the rate distortion theory on the one side, right, where you want to send information reliably in order to, say, minimizing some distortion function at some optimal rate. But, I mean, there's the other side of the story is to do all this dynamically, right? I mean, Shannon had this model of reliable communication, which is minimized probability of error. But you may want to use the channel for other things. Like if you want to use the channel For control purposes, then this sending information at a rate below this capacity that Professor Tishby mentioned is not necessarily the right criterion. It could be something else. Or you may want to use the channel for different purposes. You want to schedule the channel for sending information for different purposes, right? In that case, Shannon capacity is not necessarily the right characterization of the channel. In particular, suppose the information or the source that you have is an unstable source. Say it's a one-step, say, Markov process, right? xt plus 1 equals alpha xt plus noise wt, with alpha, say, greater than 1 or something like that. In that case, if it's an unstable source, then you cannot allow infinite delay because you will lose the source already. So what is the characterization of the channel if you want to transmit an unstable source? And my former student Anand Sahai's thesis looked at that situation and defined something called the anytime capacity of a channel. And roughly speaking, anytime capacity refers to the fact that the decoder must act at a rate which is faster than the rate at which the signal goes unstable. And that's related to the theory of error exponents or large deviations, and that's something I will not talk about. So there are many different aspects of this relationship between the information and control, of which I'm trying to talk about one particular thing. Now, also I won't talk about this. It seems to me that understanding information theory in the Shannon sense suitably modified because of this dynamical view and the issue of delays, etc. I mean, that has things to say about adaptive control and so-called self-tuning regulators. Namely, how does the organism maintain equilibrium by interacting with the environment in some sense. Okay. Now, there's during the Turing centennial, okay, so there are 2 points that this slide tries to make is that, as I understand it, biology and neuroscience, it's not just about reliable transmission by itself. It's what you're going to do, how you're going to act on the information that you're gathering or sensing and maybe doing processing, etc., in order to achieve certain actions. So so you've got to understand you've got to understand the interaction between, let me call it, sensing and statistical inference on the one side and control. So that's the first point. And then there are, and what should be the nature of models of communication, say, in neuroscience? I mean, how does the brain, in some sense, right, converts information about the sensory world, like, for example, the geometry of the sensory world, into ensemble of neural coding. By the way, I'm going to talk mainly about diffusion processes, but you could do a theory of so-called modulated point processes, a whole theory of information related to that also. Okay. Yeah, so during the Turing centenary, Sidney Brenner, the great biologist, for his famous work on the C. elegans, they worked out the whole neural architecture of the C. elegans. And he made an interesting comment as to what aspect of Turing's work might be relevant to biology, and he speculated that one of Turing's theorem is that there is a universal Turing machine which can simulate any other Turing machine. And he has speculated that this idea has relationship to the fact that in cell biology, that there's the model, right, of the cell itself built into the cell itself in some sense. And in control theory, there's something called the internal model principle, which in its elementary form says that if you want to do regulation, so you have some disturbances coming into a control system, and you want to regulate, that means minimize the effect of the disturbance on the system itself, then it must be that the controller has a model of the disturbance itself. So there are more general versions of this. So maybe Brenner's idea has relationships to work in control, which needs to be worked out. Okay, so that's the introductory part. And now I'm going to give this specific example of Landau's principle, the second law of thermodynamics, and its let's say its modern versions, which brings into information in the picture. Now, here is just one slide that the concept of information which is related to mutual information that plays an important role in a dynamical setting is this idea of directed information, right? Or the so-called or transfer entropy, as physicists have defined. And what it is really it measures the interaction between the past of a stochastic process with its future. Right? And I've defined it there. Right? So the x1 up to xn is the input. And that's really conditioned on the past of the observation, the past of the measurements, right? Y1 going only up to yn minus 1. So causality is built into the picture. If you want to deal with feedback at all, then you must pay attention to causality. Okay. And there's a concept of sort of a variation on that due to Schreiber, transfer entropy, and you will see that in a specific example in a couple of minutes. Okay. So this is a paper that has appeared recently of Nigel Newton, which works out this dependency between stochastic processes in quite a bit of generality in the Gaussian case, and that's certainly going to be important. Okay, so I'm going to essentially give a summary of what's in this paper. So this is related to what Professor Tishby showed, that it works out what is the maximum work extraction. So you have thermal fluctuations, I'll describe this in a minute, and you want to extract work. And it answers the question, how much of the work, what is the maximum amount of work that you can extract by making measurements and controlling this uncertain system in some sense. So extracting energy from thermal fluctuations. And the point of this is it works out in a finite time setting. So it's a non-equilibrium setting in some sense. Okay, so let me show this example. So here is one thing that I want to signal is that sort of given an energy function, a Hamiltonian, then you can define the free energy related to the Gibbs measure as the average energy and the entropy, right? So there's a way of stating, for example, in Bayesian inference that I've done in other work, which also explains this duality between filtering or estimation and stochastic control as minimization of a certain free energy. So it's a first order Gauss-Markov process, right? So it's really x dot equal to, say, alpha x of t plus w of t, which is some white Gaussian noise. So it's a simple linear first order Markov process, and the embodiment is that of an electric circuit with a noisy resistor, right, which is a Nyquist-Johnson resistor at a certain temperature T. And there you can, what is accessible to you is and there's a capacitor, it's a first order system, so it's an RC circuit, so you can measure the voltage across the capacitor, right, make a noisy measurement of the voltage across the capacitor, and you can intervene. You can inject, for example, current into the noisy electric circuit. I mean, that's all you have to know. It's a first order electric circuit, and you have a noisy resistor, so there are fluctuations. And what the controller does is which is the demon, which is injecting current into the system, right, in order to extract work. And the question is, what is the maximum amount of work that it can generate? Okay. And it turns out that the maximum amount of work that it can generate is related to this transfer information, right, between the source, which is the initial condition, and the noise entering to the electric circuit into the measurements. So this is the problem, that we must show how a demon can optimally control the work extraction by carefully exploiting the measurements we measure and properly choosing the injected current I. And intuitively, it's a first order noisy circuit. Intuitively, it's clear that it can create a positive work rate if it chooses I less than 0 when it correctly estimates V and vice versa. But how the demon should estimate V and how to optimally choose I may be less obvious. And right. And the essential idea is that this right, I mean, this is related to what Professor Tishby is saying, that somehow you've got to extract the right amount of information from this noisy source and use that information, right, optimally in this case, to extract work. And that's where the separation theorem comes into the picture. A priori, it's not clear that the construction of the sufficient statistic, right, from the noisy measurement and the control, namely injection of the current into the system in order to extract work, separates. So but the separation theorem, however, says that that optimally, architecturally, you have nothing to lose if you separate the filtering and the control. Now the thing is, what is the filter doing? Right. it's extracting information, right, from these noisy measurements. Well, what is the nature, and it's doing this dynamically, right? As observations come in at every instant of time t, right? So based on past information, it is creating this information. And that is the mutual information of the transfer entropy. And that's the, if you like, in some sense, the information-theoretic explanation of something like the Kalman filter. Right? So the way I want you to think about it is the filter, right, or the predictor is a map from the past and perhaps the initial state into an estimate of what into the best estimate of the scene that you have, right? That's what the filter does. That's what's at the map. And the question we want to ask is, what is the nature of this map? So I'm posing this as a dynamical systems question. Is it conservative, this flow, right? Or is it dissipative? And the answer is that it's dissipative, and I'll go to the next part of the talk, which tells you what the nature of this dissipation is. Okay, so here the picture is that think of excess as a Markov process, and that's not accessible to you directly. Can you hear me at the back? Yeah. So excess is a Markov diffusion process satisfying some stochastic differential equation, and you cannot see it directly. You see some nonlinear function of that diffusion process plus white noise. That's what Y is. Okay? Now, what I've said is that, so what you're doing is you're watching, what is accessible to you is YT, say from 0 to capital T. So this is, in my case, this is this noisy trajectory of this noisy voltage measurement, right? And what you're interested in is constructing the best estimate of xt given these noisy observations, right? Now, so what we want is this best estimate we know from theory is the conditional distribution of the state given the observations. So we want a dynamical description of this conditional distribution, and that's what psi is. Right? If there were no observations, then what you would get is the evolution of the probability density, say, of x itself, which will be some Fokker-Planck equation. Here, it is a nonlinear partial differential equation, right? So you have the Fokker-Planck equation. You have to correct for it from the fact that you're making observations. That's what psi is, and the answer is. So this is what I've written down, is that. So this is the filter is the conditional distribution of the state at time t given the observations from 0 to t. If you were interested in the predictor, then t would be, a particular s would be, say, is greater than up to t. Right? After time t, you're getting no other observation. So is this flow conservative or dissipative? And the answer is it's dissipative. And so if you have something dissipating, there's something called the stored energy roughly speaking, something that's equivalent to the internal input energy and something that's the output energy. So the input energy should be greater than the stored energy plus the output energy. So in this case, what is stored? Well, what is stored is that information that is relevant to the filter at time t. You're making observations over 0 to t. Right? So that's what C of t is. And there's the supply of information. That's the input information, the total input information that's available to you. That's what S of t is. And the difference is the dissipation. And the interesting fact is that this is all computable. In the Gaussian case, you have an explicit computation this in our papers. And this d dot of t, which is the dissipation, it's a measure of the rate at which x forgets its path. That information that's not relevant to the filter or the predictor itself, and that's computable, and that's given by the Fisher information. Now, I want to make one last comment, is that I've looked at the part that is the estimator or the filter or the predictor, right? And then you're going to use this information in order to do some control. That's where the separation theorem comes into the picture. But there's a loop there, as you might remember from Professor Tishby's talk. There's a feedback loop there. Namely, the control affects the observations, and the observation affects the control, and you've got to understand that feedback loop. So if there were control present, then the filter, the control action enters the filter itself. And that's another question for another time.